Well, happy Columbus Day and Indigenous People Day, whichever you prefer. Today we're going to do Chapter 5, but before we do Chapter 5, let's talk just a little bit about exam number 1. Exam number 1 wasn't that bad, actually. High score was 94, average in the upper 60s. Blackboard will give you numbers on things that don't matter at all. It'll give you a grade sometimes. Ignore all of that. The only thing you need to worry about on Blackboard is your total score. Now, I can never see what you see. This is the closest I can come. But somewhere when you do my grades, you should get something that says total. That's what you want. If your total right here is 175 or more, that means you have a very comfortable A right now, and it's very likely you will get an A in the course. Yes. If you're below that, please make sure you do lots of tutorials and bring it up. There were 2 problems that gave people trouble, and I'm going to go through them very quickly. This one was the Lewis structure. Compound C3H4 has 1 carbon-carbon triple bond. I'm going to do this first by way, which is kind of freestyle, and then we'll do it by the rules. So, carbon is here in group 4, has 4 valence electrons, hydrogen in group 1. Put them up there, 3 carbons and 4 hydrogens. Now, the problem says we have a triple bond. Has to be between the carbons. So let's just start off by taking a couple, move them in, make a double bond, grab 2 more, and make our triple bond. Now, we have 1, 2, 3, 4 unshared electrons on carbons, and 4 unshared electrons on hydrogens. Simply put them together. This carbon has 8 valence electrons, so does this guy, and so does this guy. Every hydrogen has 2. Convert this to line bond structures, and we have the organic compound propyne. Now that's freestyle. Let's do it again by the rules. Rule number 1, count valence electrons and hydrogens. Carbons here, hydrogens there. We have 4 valence electrons on each of the 3 carbons. So that's 12, plus 4 more is 16. Okay. Second rule, define a central atom, put the other guys on it, and give them 8 electrons. Central atom, 8 electrons. Now, place any remaining electrons on the central atom, well, we're out. That's all 16. So, make double or triple bonds. We know it has a triple bond, so let's just grab this and this, move them in, and make that. Finally, the rule says add hydrogens. Hydrogens are going to go where we have 2 unshared electrons. So 1, 2, 3, 4. And we're back to propyne. Any questions? Seems so simple now, doesn't it? It does. One more gave us problems, and that was this guy. We have 6 times 10 to the 23 moles. How many particles? Well, we all remember Avogadro told us 6.02 times 10 to the 23rd particles per mole. We start off with our given. That was our ratio. Should be an exponent, sorry. Moles cancel. And we wind up with 36 particles. Any questions? All right, well, let's do chapter 5 then. This is what's called the thermite reaction. It is so neat. These are sparks flying everywhere. I used to do this as a lecture demonstration. People in the first 2 rows would always get burned, but it was fine. They didn't mind. It's a reaction between aluminum and iron trioxide, and we'll talk more about this later. Well, we said elements undergo chemical change, specific ratio, we get a compound. Everything changes when we make the compound. Chemical change, we define as reactants and products, and we use our reaction arrow. Again, we said the reaction arrow has the properties of an equal sign. So you must have the same numbers and types of atoms on both sides. Here we have 2 aluminums, we have 6 bromine atoms, 2 aluminums, 6 bromine atoms. Physical state. See the little S's and L's and stuff like that? That stands for the physical state of the reactant. S is solid, L is liquid, G is gas, AQ means it's dissolved in water. They're optional, but sometimes they help you understand a reaction better. In order to make sure we have the same numbers and types on both sides, we stick in coefficients. Coefficients are the big numbers in front. The coefficients describe what we'll call the stoichiometry of the reaction. It's a wonderful word. You can tell people, yes, we talked about stoichiometry. They'll be impressed. Basically, though, it's just the numbers. We can interpret the stoichiometry in terms of numbers of moles. So we say 2 moles of aluminum, 3 moles of bromine, 2 moles of product. Whenever we do moles, we can also convert that to mass. 54 grams of aluminum, 479 grams of bromine, 533 of product. If you can do math in your head quickly, you have noted by now that this plus this equals this. The mass of reactants must equal the mass of the products. It's conservation of mass. We'll talk about that later. Any questions? Well, the first question should be, where do these magic coefficients come from? And this is how we do it. What we do is we look at the equation. Now, this equation is not balanced. We have 2 hydrogens here, 2 hydrogens, that's good. 2 oxygens, but here we have 1, 2, 3 oxygens. The sum of the oxygens are odd on this side and even on this side. What I try to do is come up with either all odd or all even. All even is usually easier. So we want an even number of oxygens on this side and even on that side as a first step. Now there are other ways to balance equations. There are fancy algorithms, there are computer programs, but this works. So To get an even number of oxygens on both sides, we can put a 2 in front of our water. That will give us 2 oxygens. 2 oxygens, that's 4. All right. Now, after you do your first step, you look to see what damage you've done. What we've done here is we have put 4 hydrogens here now and 2 oxygens. On this side, we have 2 hydrogens and 2 oxygens. If we double the hydrogen peroxide, we now have 4 hydrogens, 4 hydrogens. 4 oxygens, 1, 2, 3, 4 oxygens. Equation is now balanced. That's all there is to it. Are there any questions? Well, let's go ahead and look at an old exam problem. Now, I tested several things in this. The first was nomenclature. I gave it just as this, and they had to write the basic equation. We all remember now chlorate is ClO3, and it's -1. Potassium, of course, is +1, so there's KClO3, and it's solid. We're going to make oxygen gas. We remember oxygen exists as 2 oxygen atoms stuck together, so that's O2. Finally, we're making potassium chloride, +1, -1, simply KCl. That's our basic starting equation. Now, let's do the odd-even trick. We have 3 oxygens, we have 2 oxygens. Let's start off by making oxygen equal or even on both sides. Simplest way to do that is to put a 2 in front of the potassium chlorate. Now, when we do that, the damage we have done, we have now made 2 potassiums, 2 chlorines, but we have an even number of oxygens. We have 6 oxygens to be exact. Since they come as pairs, we need a 3. We also had 2 potassiums, 2 chlorines, so we need a 2. And by George, it's balanced. Now, this particular reaction is kind of a neat reaction. It's useful in lab because we have solid potassium chlorate, we heat it up, and we get oxygen gas. Nice, clean reaction. If you need a little bit of oxygen for something, it's a nice way to do it. Here's an example. This is a gummy bear. Okay, looks cute. Gummy bear is almost entirely sugar. So, sugar in the presence of oxygen and heat is going to react, it's going to decompose, form CO2 and water. The reaction itself looks like this. Sugar, lots of oxygen, CO2, and water. It's a carbohydrate. So, the gummy bear undergoes what is classically known as the gummy bear reaction. What you do is, you take a tube of potassium chlorate and heat it up. Take the little animal and drop it in. Don't show this to small children. And the poor little gummy bear slowly disappears, winds up as CO2 and water, And there's the leftover potassium chloride. Kind of a neat reaction. Any questions? Well, then let's try balancing some. Okay. This is going to be difficult. Let's do red. Yep, it's working. All right. We have 2 hydrogens. We have 3 hydrogens. Odd even. Let's start off by making the hydrogens even by putting a 2 in. We now have 2 nitrogens. 2 nitrogens, that was good. And we have 6 hydrogens, only 2. I believe, whoa, how did that happen? If we put a 3 in here, it'll work. Yep. Any questions? Our next one. 1 zinc, 1 zinc. 1 chlorine, 2 chlorines. Let's go ahead and fix that with a 2. Now, that gives us 2 hydrogens, that's what we have, and also 2 chlorines, and that's what we have. And by George, I think we're there. Iron 3 oxide reacting with chlorine gives us iron 3 chloride and oxygen. Okay. Let's see. We have 3 oxygens, 2 oxygens, right? So let's double this guy. Now, that gives us 4 irons. So we need a 4 here. And it gives us 6 oxygen, right? So we need a 3 here. How many chlorines do we need? We have 3 times 4. That's 12. They come as pairs. So that should be a 6. Let's see if I got it. Yep. Any questions? Then why don't you try to do these? And then we'll look at the answers. We have 2 hydrogens in the first one. We have 3 on this side. Simplest way to fix that would be to put a 2 in here. Now that gives us 2 sodiums. We only have 1 on that side. So let's fix that. So 2 sodiums, 2 sodiums. 2 hydrogens, oops, 4 hydrogens. So we need to double this. And that gives us 2 oxygens, and we have 2 oxygens there. So I think that should work. Yep. Do the next one. We have one lead, one hydrogen, two hydrogens. So let's fix that. The damage, we made two chlorines, but by gosh, that's what we need here. I think with that one simple thing, we did it. Now, when you're dealing with things with polyatomic ions, don't break these down into individual elements. Just treat it as a lump, as nitrate. It's a little ball, okay? We have one silver, one silver. We have one nitrate, we have two nitrates. So we're going to have to fix that with a 2. That gives us 2 silvers. Need another 2. One magnesium, 2 nitrates, 2 nitrates, 2 chlorines, 2 chlorines. I think that's it. By gosh. Any questions? Takes a little bit of practice. Practice in this class, of course, means tutorials. Here's a, oops, let's get rid of that. Somebody wrote all over my screen. Well, keep trying. Okay. When you hit new reaction here, you will get a reaction. On the website, each of these has a little field in front of it. You just type in a number. Blackboard is the same thing. The only thing, remember, Blackboard will not take an empty field. It's always wrong. So will this. So you have to put a 1 in if the coefficient is ever 1. So this is the organic compound ethene. Reacts with oxygen to give CO2 and water. Right away we see we have 2 carbons and only 1. So let's double our carbons. We have 1, 2, 3, 4 hydrogens, only 2. Let's double that. We have 2 oxygens, 2 oxygens. Oh, I forgot. And we have to put the 1 in for the ethene. Any questions? Now, as you do these for practice, some of them get a little strange. If you get a really strange one, just do a new problem again and get one that looks better to you. Here's another one that's actually a fun reaction. This is calcium carbide. Calcium carbide reacts with water to form acetylene and calcium hydroxide. Acetylene burns. It's in acetylene torches and stuff like that. Calcium carbide is a convenient little solid. And of course, water is a liquid. Back in the old days, old days, before electricity, when miners went down in mines, they wore little hats like this. Had calcium carbide in a thing here, a little bit of water, push a button, they mix, and you light it, and there's your acetylene. Considering all the explosive gases in mines, it's amazing anybody survived. Okay, so let's go ahead and do this. 2 carbons, 2 carbons. 1 calcium, 1 calcium. We have 2 hydrogens, 1, 2, 3, 4 hydrogens. We're going to have to fix that even though it's not odd even. Fix it with a 2. That gives us 2 oxygens, and we have 2 oxygens as well. Very simple equation to balance. Any questions? Well, in addition to trying to explode minors, calcium carbide plus water was part of my youth. In the 50s, you used to be able to buy things like this. It's a cannon, okay? About that long. And you had calcium carbide in here. Push the little button, you had water in the bottom, it would fall in and make acetylene. This guy, when you push it, made it spark. And it goes boom. Kind of really neat. You could put all sorts of stuff in the barrel here, and it would shoot it halfway across the yard. Really kind of neat. That's just how we do work. Any questions? Now, the only way to really know about balancing equations is to do it. Tutorials help. Blackboard helps a little. These guys, this is a balancing worksheet, no credit, but print it and just try it. The answers are there too. So if you want practice, it's a nice way to do it. Any questions? All right, well, let's continue talking about reactions. We're going to start off with something very biological. We're going to do the taxonomy of chemical reactions. Let's break it down into types. The only reason to break it into types is because that makes it easier to predict products when you're going the other way. So let's just bear with this. Synthesis and decomp. Synthesis reaction, not surprisingly, we make one or more new substances. An example, if you take carbon, react it with oxygen, you get carbon dioxide, new substance. Think a barbecue pit. They burn. These are elements called synthesis from the elements. We can also do synthesis from compounds. Again, this is the organic substance ethene. If you react this with hydrogen bromide, you add hydrogen to one carbon, bromine to the other, and we make ethyl bromide. This is synthesis from compounds. Again, you can do either elements or compounds to get stuff. Decomposition. Simply synthesis backwards. This is copper 1 sulfide. If you take copper 1 sulfide and heat it up, by George, you get copper metal, and sulfur. Since you're heating it, the sulfur usually burns, goes away, and you're left just with copper. In Europe, this ushered in the Bronze Age, because now you could very easily make metal out of rock. It was amazing. Apparently in Minnesota, I believe, there are large deposits of simply pure copper. That's because the copper 1 sulfide was heated by a volcano, and it all decomposed and just left copper laying around. But Europe, it was all copper sulfide. Decomposition into elements. We can also decompose into compounds. Calcium carbonate, if you heat it up, will give calcium oxide and CO2. This reaction actually is very important because it goes backwards very easily. If you take calcium oxide, mix it with water, it will absorb CO2 from the atmosphere and make calcium carbonate, also known as cement. That's how you make cement. We did something like this in lab. We took ammonium hydrogen carbonate, heated it up, got ammonia, CO2, and water, and smelled this stuff very carefully. Decomposition into compounds. Any questions? Replacement reactions. There are two varieties, single and double. In a single replacement, you will take a metal and an element, and a compound, and you will make an element and a compound. But you replace, in general, if your element is a metal, it will replace the metal in the compound. If it's a nonmetal, it will replace the nonmetal. That's a nice, happy general rule. Metals replace metals, nonmetals replace nonmetals. Single replacement. The other type is called a double replacement. Oh, we did this in lab. Remember, we took our nail, put it in with copper nitrate. When we did that, we wound up with copper metal, deposited on the nail, and iron 2 nitrate in solution. The other type is a double replacement. In this, you have solutions of your reactants. So this happens in solution. And what simply happens is you will swap ions between your reactants. So the silver pairs with the chlorine, the sodium pairs with the nitrate. This reaction only happens if you have something formed that's insoluble, solid silver chloride, or if you have a gas form. We'll talk about this in a bit. Finally, redox reactions, oxidation and reduction. In these reactions, we have a change in oxidation number. Now, when we did nomenclature, we talked a little bit about oxidation number. We'll talk more today. But for example, carbon reacting with oxygen gives CO2. We saw this, right? Remember back in chapter 3, I think it was, we said that elements have an inherent oxidation number of 0. And that oxygen in a compound was going to be -2. So here we have 4 negatives. That means that the carbon to be neutral must be a +4. The oxidation numbers have changed from 0 to +4 and 0 to -2. That makes it a redox reaction. Again, we'll talk more about that. Any question on the simple nomenclature? Well, let's just do a couple. Here we have hydrogen reacting with nitrogen to make ammonia. We are taking 2 elements. We are making a compound. This hydrogen, we are making a compound. This is clearly a simple synthesis. This will also be a redox reaction. We'll talk about that when we do redox. Lead 4 chloride with fluorine is lead 4 fluoride and chlorine. The nonmetal has replaced the nonmetal. This is a single replacement reaction. Here we have aqueous solutions of sodium sulfate, barium chloride. When we mix them, we get solid barium sulfate, and we get sodium chloride in solution. We have simply swapped ions, sodium for chloride, barium for sulfate. It's a double replacement reaction. Let's do another. Look at these, figure out what they are, then I'll talk. We're starting here with hydrogen peroxide in solution, and we are making oxygen gas and water. We are decomposing the hydrogen peroxide, simple decomposition reaction. Put this next one on an exam once. A whole lot of people missed it. Okay? They said this was single replacement because we have an element and a compound, but a single replacement must yield an element and a compound if we just have a compound. This is nothing more than a simple synthesis. And here we have an element and a compound, element and a compound, the hallmark of a simple single replacement. All right, now I said the only real reason to understand the nomenclature here is because it makes it easier to predict a reaction. Let's go to a reaction that we've seen many times. Aluminum metal reacting with bromine to give aluminum bromide, of course. When you have a reaction like this, it's a synthesis reaction, and we have a metal. What you want to do is to look at the common charges. So we take our aluminum, add it to bromine. Fun thing to do. We know a reaction is happening because we see fire. We see huge plumes of toxic vapor coming out. And we wind up with a substance up here that has totally different properties than what we started with. So this, we said, was going to be our product. What is it? Because aluminum is a metal, it will most likely form a +3 ion. It's group 3, right? Bromine. Bromine is it's a halogen, so it's almost always going to be a -1. We need 3 bromines for every aluminum. That's our predicted product. But is the equation balanced? Well, of course not. So go ahead and balance the equation. Aluminum looks good, 1 and 1. But we have 3 bromines and we have 2 bromines. So let's double this guy. Now we have 2 aluminums and 6 bromines. We need a 2 out here. And to get 6 bromines, we need 3 here. Any questions? On your exam, yes, you will get to balance an equation, just so you know. All right, let's do another. Here we're dealing with two nonmetals reacting. No metal in the reaction. When you're doing nonmetals, you look to see how many valence electrons you're dealing with, and then put them together in a logical way. This balloon has hydrogen, the room has oxygen. Again, they react so nicely. Hydrogen has one valence electron. Oxygen is group 6. So it has 6 valence electrons. We put them in as 2, 2, and 1, 1. Our predicted product is therefore going to pair up these guys and simply be water. Any questions? Nonmetals, you see how many valence electrons. Metals, you do charges. Oh, I forgot. Ignore those numbers. This is not balanced either, is it? We have 2 hydrogens, but only 1 oxygen versus 2. So let's double our waters. This gives us 4 hydrogens. We have 2 on this side, simply double it. I believe that works. Now this we haven't seen before. It's one of my favorite reactions of all time. It's a decomposition. Now the problem with a decomposition is darn near anything can happen. You really have very little clue what's going on. You need to do the reaction and look for clues. This is nitrogen triiodide. It is a contact explosive. So it decomposes very easily. This stuff is incredibly easy to make. You take ammonia and you take iodine. Simply mix them together and this black stuff falls out of solution. While it's in the water, it's no problem. You take and run it through filter paper and you wind up with a black spot in the middle of your paper. Let it dry. Now, what we're going to do here is to come in and very carefully disturb this bottom layer. We're going to do that. I said it's a contact explosive. We're going to do that with a feather. Literally touching it is all it takes. Now, to try to figure out what's going on, you do the reaction, it's fun, and then you observe. What we observe here is this explosion and the formation of this big purple cloud. Well, what's purple? Iodine is purple. And it has a very high vapor pressure, so it gives off purple fumes. The best guess here is that this is iodine as I2. Probably decomposition into elements. Nitrogen will give us N2, iodine I2. Now once again, go ahead and balance it. iodines, only 2. Let's double out here. That gives us 2 nitrogens, so that's what we need. We have 6 iodines, so we need 3 of these guys. Any questions? So, synthesis reactions, you look to see if you have a metal or a nonmetal. Decomposition reactions, you look at the products, give it your best guess. Redox reactions, replacements first, okay. Single replacement, we remember the rule. Metal replaces metal, non-metals replace non-metals. Again, we're looking at a compound and an element, and we're going to make a compound and an element. Fluorine is a nonmetal. It will replace the nonmetal in lead 4 chloride and should form chlorine. Lead is +4, it won't change. Fluorine will replace the chlorine. Okay. Now, is this equation balanced? Nope. Nope, it's not. Here we don't have odd and even. We just have something that doesn't work. We have one lead, that's good. 4 chlorines, only 2 chlorines. For 2 fluorines, 4 fluorines. Let's start off by doubling our fluorine to give us 4. We have 4 chlorines, we need a 4 or 2 here. We have 1 lead, 4 fluorines, 4 chlorines. I think we're good. Any question? There are exceptions, of course, because this is a rule. Sadly, the most important single replacement reactions industrially are the exceptions. So, they involve hydrogen gas or carbon, and they're used in refining. If you take copper to oxide, expose it to hydrogen, you will get copper metal and water. Looking at our balance, we have 2 coppers, 1 oxygen, and 2 hydrogens. So the balance is good. This is how they make copper metal industrially. This guy, iron 3 oxide plus carbon. We have 4 irons, 3 carbons, this works. This is how they make iron industrially. Hydrogen and carbon are both acting as metals, even though they're not. That's why it's called an exception. This reaction is important industrially because this is what they do in Gary. Take iron 3 oxide, carbon, heat them up together, and make molten iron. Any question? I won't try to trick you, I promise. All right, double replacements. Again, I said these are reactions in solution. Okay? In order for the reaction to go, something that's formed must be insoluble. Here we have potassium sulfate, barium nitrate, In a double replacement, we swap ions, so we'll get potassium nitrate and barium sulfate. We predict that barium sulfate will form. It will be insoluble and precipitate. The potassium nitrate we form will stay in solution. So we predict the products will look like this. Simply swap the ions, and one guy is insoluble. Here's another little video of a reaction like that. Potassium iodide reacts with lead nitrate. We swap ions. We get lead iodide and potassium nitrate. Potassium nitrate stays in solution, and this comes out as a solid. These are both clear liquids when we start. Pick up a squirt of one of them, add it to the tube. We get an immediate precipitate, it's called, of lead to iodide. If you let this sit long enough, all the solid particles will collect in the bottom of the tube. Any questions? Well, one question should be, okay, but how do you know that lead to iodide is going to be a solid? Same thing with barium sulfate. How did I know that? I knew that because I know the rules. Rule 1. If you have a group 1 metal or ammonium and you make a product, it will be soluble in water. Group 1 metals and ammonium, always soluble. Rule 2. If your anion is a nitrate or an acetate, doesn't matter what the cation is, it'll be soluble. So far, they're very simple. If you have a metal halide, remember the halides we worry about are chlorine, bromine, iodine, they will be soluble, except for the ugly 4 here. We call these heavy metals: lead, silver, mercury, and copper. These will all be insoluble. Sulfates are very similar. Metal sulfates are going to be soluble except barium, lead, and calcium. Those are insoluble. Finally, if you make a hydroxide or oxide or sulfide, it's going to be insoluble unless Rule 1 dictates. Got it? Let's see if we have it. Oh, there's one more. Metal carbonates are insoluble, again, except for Rule 1. So we have insoluble, 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 soluble, soluble. 4. Let's see. Start off with this, guys. Silver nitrate. What do you think? Silver, we said, was one of our heavy metals, wasn't it? It's a bad guy. But this is a nitrate. What did we say about nitrates? They're soluble. Doesn't matter what you stick it with, nitrates are soluble. Here we have a metal halide. Rule is metal halides are soluble except for silver, lead, mercury, copper. This is magnesium. It'll be soluble. This guy, sodium sulfate. We know that there's a problem with sulfates, right? Some metal sulfates are not soluble, but this guy has a sodium in it, doesn't it? Rule 1, going to be soluble. Again, the sulfates that are not are barium, lead, and calcium. Back to silver. We said silver was a heavy metal. Most metal halides are soluble, except for silver, lead, mercury, and copper. We know that barium is a bad guy, right? But that's only with sulfate. This is a nitrate. Virtually all nitrates are soluble. We just saw beautiful lead to iodide being formed. It forms because most metal halides are soluble, except for silver, lead, and mercury, and copper. It's a nitrate. We know this by now. If it's a nitrate, it is soluble. Here's our guy, barium sulfate. We know that most sulfates will be soluble, but barium is an exception, and it's insoluble. Barium, lead, calcium. Metal halide. Iron is pretty heavy. You would think it would be a heavy metal, right? It's not. Heavy metals are restricted to silver, lead, mercury, and copper. And finally, what in the world is this thing? It's the organic polyatomic acetate. Oh, you will become very familiar with acetic acid and acetate in general chemistry. But right now it's just an acetate. And as an acetate, it'll be soluble just like a nitrate. So what do you really have to know here? Basically, the ones that you will see on the exam and stuff would be things like silver chloride, barium sulfate, sometimes lead iodide. Those are the big guys. Just kind of remember those. All right, let's see how we do this with a double replacement reaction. Here we have solutions of silver nitrate and potassium carbonate. We're going to mix these. We are going to make silver carbonate and potassium nitrate. Now the nitrate's going to be soluble. But remember the last rule down there? Carbonates are not. Silver carbonate, we predict, will be a solid. The equation isn't balanced. Go ahead and fix it. We have 2 silvers, 1 silver. We needed 2 out here. That gives us 2 nitrates. Only have 1. Need 2 nitrates. 1 carbonate, 1 carbonate. I think we're good. Look at the next one. Again, it's a carbonate. We're going to swap ions. Copper to carbonate will be insoluble. Potassium nitrate will stay in solution. Check our balance. One copper, 1 copper. 1 carbonate, 1 carbonate. We have only 1 potassium. Have 2 here, let's double that. That gives us 2 nitrates, 2 nitrates. I think we're done. The next one, aluminum carbonate, will be our solid. Again, potassium nitrate will stay in solution. We have 1 aluminum, 2 aluminums. Let's double it. We have 3 carbonates. Only 1. G. Oh, I'm sorry, this also gave us 6 nitrates, so we need 6 of these guys. Carbonates. We need 3 of them here. That gives us 6 potassium, 6 potassium, 2 aluminum, 2 aluminum. I think that's it. Mix it up a little bit, and you guys work on this set for a second. First, decide what's going to be insoluble. Write your equation and then balance it. We are going to make magnesium nitrate. That will be soluble, of course. We will also make silver chloride. Most metal halides are soluble. Silver chloride is not. We are going to need 2 silver chlorides, so we have 2 out here. Nitrate is a -1, magnesium +2. So the 2 here will suffice. 2 silver chlorides, 2 silver nitrates. Yep, that worked. Sodium nitrate will be soluble. Barium sulfate will not. We are going to need 1 sulfate for every barium, 1 nitrate for every sodium. I don't think you have to do much to this equation, except write it down. 2 nitrates, 2 nitrates. 2 sodiums, 2 sodiums. Finally, remember, we said oxides, hydroxides, and sulfides are all going to be insoluble, unless Rule 1 took over. Here we have lead sulfide. That will be insoluble. Sulfide is -2. We're going to need 2 leads. We have 2 sodiums, 2 nitrates. I think we simply need to, just double the nitrate, that's all. Yep, that'll work. It's lead 2 sulfide, so that's okay. Any questions? All right, so I'm sure everybody is now anxiously awaiting redox reactions. Redox reactions involve transfer of electrons from a donor to an acceptor. When one element goes an increase in oxidation number, it's called an oxidation. When it decreases, it's called a reduction. The simplest way that I find to remember that little rule is just to say oxidation is the loss of electrons. We'll see how easy that is to apply in just a minute. Remember, oxidation numbers. Start off with the periodic table. Everything here is 0. By definition, everything as it sits is a 0. If you have a metal in your compound, binary ionic compound, the oxidation number is the same as the charge. Magnesium here is +2. It's group 2. Bromine is -1 because it always is. Oxidation numbers are +2 and -1. Just the charge. Lithium phosphide. Lithium group 1 +1. Phosphorus -3. Oxidation numbers are the same thing. So elements are 0. Metals are simply the charge. For the other atoms, you need the rule. Rule 1, element is 0. Metals, +1, +2. Fluorine is always going to be -1. Then it gets a little iffy. If hydrogen is bonded to a metal, it's -1. Generally, it's always +1. Oxygen is -2. We know that one from chapter 3. Halogens are -1 unless they're bonded to oxygen. Sulfur and selenium are -2. Now, nobody likes rules, but again, on the second hour exam, you get a 3x5 card. If you want to waste it writing all these rules, you can, because you will have oxidation number questions on the exam, I promise. And it could look something like this. Here we have sulfur trioxide. It's molecular. Sulfur trioxide. Oxygen, we know from chapter 3, is always going to be a -2. This gives us 6 negatives, right? To make this neutral, that means the sulfur must be a +6. That's simple. Let's do another one. HNO3, this is called nitric acid. We will use this as well. Got to be really careful with it because it burns your skin easily and leaves big, ugly splotches. So, here we have an oxygen. It'll be a -2. This is what the thing looks like. The hydrogen is bonded to an oxygen, so it will be a +1. So, oxygen -2, hydrogen +1. This gives us 6 negatives, 1 positive. To make it neutral, we need 6 positives. The nitrogen must be +5. Any questions? Well, of course there's a tutorial. Fairly simple and fairly similar to what's on Blackboard. Here you simply have to enter the oxidation number that they ask for. Lead is a metal, so it's going to be whatever the charge is, right? Nitrate we know is -1. Lead must therefore be +2. Here we have potassium hydride, phosphorus hydride, trihydride. I'll get this right. Hydrogen is bonded to a non-metal, so it will be a +1. Oxidation was +1 unless it's bonded to a metal. So this will be +1. We have 3 of them, so the phosphorus must be a -3. So +1 for our hydrogen, -3 for the phosphorus. Any questions? All right, finally, let's do recognizing redox reactions. Remember we said in a redox reaction, we will change oxidation numbers. If something is oxidized, its oxidation number will increase, as in 2 to 3. If it's reduced, it will go down to 0 to -1. Once again, what I always say is loss of electrons is oxidation. Here we have aluminum. Here we have iron trioxide. We're making metallic iron, and we're making aluminum oxide. We have a compound and an element. Compound and an element. This is clearly a single replacement, right? We start off by looking at the oxidation numbers that we have. This is an element, it's 0. This is an oxygen, it'll be -2, and that makes the iron a +3. In our products, iron is now the element. It's a 0. Oxygen is still -2. Aluminum's a metal here, it will be +3. So step 1, have the oxidation numbers change. Absolutely. 0 to +3, +3 to 0. Which element has been oxidized? Which element has been reduced? Which element has lost electrons? In order to go from 0 to a plus number, you have to lose electrons. Aluminum is oxidized, iron goes up, it has been reduced. This has lost electrons, this has gained electrons. There is confusing nomenclature that shows up about redox reactions. They involve words like oxidizing agent, reducing agent. I won't use these. They will not be on the exam. General chemistry will use it all the time because they try to confuse you. I would. But oxidizing agent is the thing that causes the oxidation to occur. That's the thing that is reduced. Iron is the oxidizing agent. Aluminum is the reducing agent. You should know those words exist. You may read them somewhere. They will not be on the exam. All right, this is the reaction that we just looked at. This is a set of two flower pots. Okay? This one has sand in it. This one has aluminum metal plus iron oxide, just mixed together. Flower pots have a little hole in the bottom, don't they, for water. What we're going to do is take a burning piece of magnesium to start this. Stuff it in here carefully and run away. The reaction will commence. Run away. As molten iron is formed, it's moved at the bottom into the center. All these spikes of little bits of molten iron. That's why the people in the front two rows always get caught. Trouble with this reaction is you never quite see when it's done. So you stay away for a long time. When it's finally done, this is our lump of white hot iron that collected on the sand. When it finally cools, you can see it looks like a lump of iron metal. That's the thermite reaction. One of the neatest reactions you can do in chemistry. We can't do it in that, but I would. The sad thing is that whenever you have something really neat like this, people often find a way to use it in bad ways. Enter the thermite bomb. Thermite bombs. You little thing, you drop these over people's homes. That happens, and you wind up without people's homes. This is from World War II, where they were very common. They're still used, even though they're outlawed. Shame. All right, look at these guys. Determine if it's a redox. Determine who was oxidized, who was reduced. We'll do the first one together. Tantalum is an element, so is bromine. They're zeros. Bromine is a halide. It'll be -1. We have 5 of them. Tantalum must be +5. Question 1. Have oxidation numbers changed? Absolutely. 0 to +5. 0 to -1. Who has lost electrons? To go from 0 to a plus, you have to lose electrons, right? That must be oxidation. Tantalum has been oxidized, bromine reduced. Look at the next one. Your oxidation numbers. Silicon and aluminum are elements, so they're 0. Aluminum's a metal, will always be +3. Oxygen -2. If oxygen is -2 here, since we have 2 of them, silicon must be +4. Yep. Now, who has been oxidized? Silicon went from 0 to +4. Had to lose 4 electrons to do that. Loss of electrons is oxidation. Let's do 2 more. What type of reaction is this? It's two compounds, so it's a double replacement. What's going to be insoluble? Sulfide is just like oxide, it'll be insoluble. So, nitrate is -1, so -1 here. Sulfur will be -2, each sodium is +1. -2 here, +2 here. So, is this a redox reaction? Have oxidation numbers changed? Nope. 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 This is not redox. Whenever you have a double replacement, redox does not occur. Double replacement, no redox. Oops, wasn't supposed to happen yet. Element, compound, single replacement, right? Hydrogen and nickel will be 0. Halogen will be -1, -1. Nickel here is +2. Nickel here is 0. Have oxidation numbers changed? Absolutely. Hydrogen went from 0 to +1. Nickel from +2 to 0. Who has lost electrons? Who went from 0 to +1? It's our hydrogen. So for practice, tutorials. Now this one is really strange because it uses a vanadium oxide polyatomic ion that we have no idea what it is. Trust me, it's a polyatomic ion. So, we're interested only in the vanadium. Has it been oxidized or reduced? Blackboard, same thing. So, in this compound, this polyatomic ion, oxygen is -2, right? Oh, also I'm supposed to point out, this isn't a complete reaction, it's called a half reaction. We won't deal a lot with those, but it's basically only the stuff that really undergoes change. Only the stuff that matters. So here, our oxygen will be -2. We have one of them, so this is -2. We wind up with a polyatomic with a +2 charge. 2 of them are neutralized here. The vanadium must be +4. On this side, we have two oxygens at -2 each. We have one plus sign left over. So this is the 4 and -2. That means the vanadium on this side must be a +5. So what has happened to vanadium? It has gone from +4 to +5. Does that mean it gained an electron or lost one? Had to lose one, right? It's an oxidation. One more. Thallium here. Again, the half reaction, that's all we care about. Starts off as +4, goes to 0. Is that going to be an oxidation or a reduction? It hasn't lost electrons, has it? It has gained 4 electrons. That's a reduction. All right, as we were doing the single replacement reactions, I'm sure all of you were sitting there wondering, how do I know if that's really going to work or not? Right? Simple way to predict it is what's known as the activity series. Now, we're not going to do a whole lot with this. Again, this is pretty much general chemistry. I just want you to be familiar with it. When you're dealing with activity series, hydrogen is right here. Okay? Not shown, but it's right there. You have two ions, or an ion that's going to react with an element. It's going to make an element and a compound. What you want to do is find the element on the table here and find the ion. So that's that. We're dealing with sodium. If the element is higher than the ion, hydrogen, reaction will occur. The further apart they are, the more vigorous it is. If the element is more active than the ion, this will occur as red. What's your prediction here? Here's the ion, here's the element. Element is here, ion is here. The element is above the ion. We predict that this will occur. This is similar to what we did with our nail. This solution here has a copper salt, copper nitrate, I think. We just put copper metal into it. No, silver nitrate, sorry. After about 2 minutes, we wind up with fuzzy copper. After 7 or 8 minutes, we have very fuzzy copper. Let this sit for a while, get lots and lots of fuzzy copper, and a blue solution. Why is the solution blue? Because copper salts tend to be blue. So this is our single replacement reaction. Element in a compound, element in a compound. Copper is more active than the ion. We'll actually do this in lab. Here's our element, here's our ion. Element and the ion. Iron will replace copper. That's why we get our copper nail. Iron is more active. Putting this in terms of a test question. If I gave you this and I asked you, which of these will occur? How would you do it? You would find aluminum and lead. Aluminum is here, lead is here. The element is more active than the ion, therefore this will happen, this will not. That's how you use the activity series. All right, let's just do a couple quick questions. Aluminum and chlorine react to form a compound. What's true? First of all, I would write the reaction. It's going to be a synthesis reaction. Aluminum reacting with chlorine to give aluminum chloride. The compound will be ionic. Of course, it has a metal. Oxidation number of aluminum in the reactants is 0. It's an element. Of course, it's 0. Molecular formula will be AlCO3. Yep, that's what we said. And this is all of the above. Which are going to be soluble or insoluble in water? We know if it's a nitrate, it will be soluble. Rule that out right away. Most sulfates are, but barium isn't. Most halides are, but lead isn't. So it's just A and B. In this number, the oxidation number of fluorine, what happens to it? Goes from 0 to -4. Well, for sure, is 0 in the reactants, right? But what is it here? Fluorine is always -1. Does not change. Well, that's stupid. -1 in the reactants? No, it's 0. And this is none of the above. Again, your exam will have something like this. Oxidation number for N2O5. We know the oxygen will be -2. We have 10 negatives. In order to make this neutral, the nitrogen must be +5. One more here, just like that. This is called chloric acid. It looks something like this. Again, the hydrogen is bonded to an oxygen, so it'll be +1. Oxygen will be -2. We have 6 negatives, 1 positive. The chlorine must be +5. All right, we made it through the chapter. Today we had 3 tutorials: balancing, assigning oxidation numbers, and oxidation reduction reactions. Again, it's 5 points for every one that you do, up to 5. Now, I always say do your tutorials, right? Some of you learned the lesson on exam 1 that, gee, I wish I would have done more tutorials. There's a very, very good reason now to do your tutorials. After you do exam 2, if the total on Blackboard is 350 or above, I will give you an A that very day, and you will not have to take the final exam. Yes, I'll say that again. 350 on your total. You will get an A in the class, no final. It is an oh my goodness moment. Twice. Do your tutorials. They're very, very important. Any questions? Some of you already have well over 200 points. You are well on your way. Do your tutorials. I was told that tutorials 2 are not up yet. I don't know why. They were supposed to be. I will fix that. Thank you. Have a good day.